you have already spent some time in Algebra 2 learning and talking about inverse functions. So some of what we do at the very beginning here is going to be some review. In pre-calculus, we look at inverse functions. We maybe go a little bit more in depth or look at a little bit more complicated versions of inverses. But the idea of inverses are still the same. So inverse functions have a special notation. It looks like an exponent of -1. So it looks kind of like f raised to -1. But when you see that, you read it, you just say f inverse. Or you could say f inverse of x in function notation. So f inverse. Does anybody remember from Algebra 2 what is important about inverses? How do you find inverses? How do you create inverses? What's the key piece to the inverse? That would be kind of like what the exponent of -1 would do. I think it's brewing in a few minds.
It's just the one where you set it equal to 0 and like resolve it.
Sort of. Zachary?
Isn't it where you're trying to find y instead of x?
Yes. What do you have to do before you start solving for the y? I think that's kind of where you're going on that. Switch x and y.
Oh. Yeah.
You switch x and y. So this works for all scenarios. If you're looking at a table of values, you switch the x and the y's. If you're looking at a graph, we switch the x and the y ordered pairs. So they become y comma x. If you're looking at an equation, you switch x and y in the equation. Everywhere you see y, you write x. Everywhere you see x, you write y. Okay? And then you go through and you solve for y. So some of us had this idea of kind of working backwards. Yes, you are working backwards. But the key piece there is that you've got to switch x and y. Now, something that we're going to pay closer attention to here in Honors Pre-Calculus is the fact that if we switch our inputs and our outputs, our x and our y, that means we should see a switch in domain and range. So the domain of f is the range of f inverse. And vice versa, the range of f is the domain of f inverse. So we're going to be asked to find the domain and range of our inverse functions and then also our original functions. They should be the same two intervals in this case, not like the compositions where we could have different ones, but they will be the same and they'll just be switched. Okay, because all we're doing is switching x and y. Okay. The last thing that we want to talk about from Algebra 2 is how we verify inverses. So now that you kind of remember that you're doing this piece of switching x and y, does anybody remember how to verify whether or not something is an inverse?
Don't you plug in the regular function f into the inverse f?
Plug the regular function f into the inverse of f. So we could say something like f inverse of f. And what's supposed to happen? It equals what? X. At the same time, what else must be true? The opposite. F of f inverse of x must also equal x. Okay. Both must be true. So to verify inverses, you basically do compositions because inverses are working backwards and you had switched x and y and solved for y, you're going to undo all the operations in the other function and you're just going to be left with x. Okay, so that's how you can verify given two equations whether or not they're actually inverses. Now, graphically, just so you understand, if you're switching x and y in an equation, or you're switching x and y in a table, or from ordered pairs on a graph, that means that you're basically reflecting an actual graph over the line y equals x. So I've got a picture of a graph up there. It looks like a cubic function that's been shifted up 1. And then I've got the dotted line there. That's the line y equals x. If there's a point xy on the graph of f, then the flipped version of that y comma x is on my graph of the inverse of f. So there will be some questions on your homework where you get a picture of a graph and you're being asked to sketch a graph of the inverse. You want to draw it so it's a reflection over this xy or line y equals x. You can also select some points on the actual graph of the original function and then just switch the x and y to get a new point on your inverse. So I'm noticing on this particular graph there is a point here, it looks like 0, 2, because I'm going by 2's. And that would mean there's a point here at 2, 0 on my inverse. And I could look for another point. I'd say, oh, like this point right here looks like -4, -6. So then I have an ordered pair -6, -4 on my inverse. You can also see visually as you plot those points by switching the x and the y. You can also see geometrically, if you were to fold on the line y equals x, these points would be mapping onto themselves. So I could draw the completed inverse. I'll go ahead and draw it in red here. Looks something like this. If I fold on the line, I'm mapping onto myself. The original looked like a cubic function that had been shifted up 1. Now my red function is a cube root function, if you'll remember those. And it looks like it's been shifted right 1. Both functions have a domain and range of all real numbers because end behavior is going opposite directions and they're continuous on both sides. Okay, so there's 2 things that we're going to discuss really quickly. I would put these things into your notes. They're terms that we did not discuss in Algebra 2. So one of them is the horizontal line test. Yes, thank you. I saw that first hour and I corrected it, but I didn't save it to my original file, so I'll have to remember that. Thank you. The horizontal line test says if no horizontal line intersects the graph of f at more than 1 point, then f has an inverse function. Key word in that test is function. If it doesn't pass the horizontal line test, f still has an inverse, but the inverse isn't another function. Okay, so the inverse itself wouldn't pass a vertical line test, where every x was equal to only one y. When you have graphs that pass the vertical line test, meaning they are functions, and then they also pass the horizontal line test, which means they have an inverse function, they're a special kind of function called a one-to-one function. And just think about what one-to-one mapping would mean. It means every x has only one y. That's the definition of the function part. One-to-one also means every y has only one x. So now, none of the x's repeat, none of the y's repeat, because every y has only one x. So one-to-one functions would be things that do pass the horizontal line test. Okay, every y has only one x. Now, we are going to use the horizontal line test because I am only asking you to find inverse functions. So if you graph something and it does not pass the horizontal line test, then you do not need to find the inverse. Okay? Because then the inverse would not be a function. You are only finding the inverse function. Let's look at some examples. If you have a graphing calculator, go ahead and get out your graphing calculator, and we'll look at quick ways to see a graph to do a horizontal line test. If you don't have a graphing calculator, you could have out your library of functions, those 8 basic functions, the pink sheet. And we'll also just kind of talk about the shapes as we graph them in our graphing calculator. So that first one that we want to graph is going to be the cube root of 7 plus x, and 7 plus x is underneath the cube root. I'm going to pull over my doc cam so you can see me entering some things into my graphing calculator. So I turn on my calculator. I'm going to go to my y equals menu, which is that button at the top left under the screen. This is where I always go when I want to graph something. Okay. You have the colored buttons for second alpha. Another really great button is the one right underneath your alpha button that says math. Okay. And math brings up a list of different types of things that you might want to use. So we want to do the cube root. You can either type 4 or you can choose 4. Notice that this in number 1 and number 2, that's how you can also change like decimal answers to fractions or fraction answers to decimals. Okay. So I'm going to go ahead and choose my cube root. Notice it brings up a set of parentheses, so anything that I put behind that parentheses is going to be included underneath the cube root. And I'm going to go ahead and type 7 plus x, so I've got 7 plus, and then remember x is my x comma t comma theta comma n. And then I'm going to close my parentheses for good measure, for good practice. That's all underneath my cube root. And I'm going to go ahead and do zoom 6 so that I get my standard viewing window, zoom 6. And it's the cube root function moved left 7. So for those of us who don't have the graphing calculator, we have studied cube root functions. So we know that that looks, I always told my students, kind of like a stretched out S. Okay, and that function just gets moved left 7 units, and then I could tell from the basic parent graph that that passes the horizontal line test.
My graph doesn't look anything like that.
Okay, I will come over in just a moment. Do we agree this passes vertical line test? Okay, so I'm going to come over and help Zachary. What I would like you guys to do right now in your notebooks is go ahead and replace f of x with y. Then switch x and y and try to solve for y. So you can talk amongst your groups if you need to. See if you can find the inverse function. Let's see. Okay, now do zoom 6. So when you do zoom 6, you're getting a negative 10 to 10 on both sides. You have probably, on that last graph, zoomed out at some point, so your calculator, every time you turn it on, it defaults to a zoomed out. So it was zoomed out, which made it look like a straight line, because if you look at that little bump is really small, right? Okay, so anytime when you're thinking things aren't right, do zoom 6. How did you get y all by itself? What sorts of things did you and your groups possibly do? Cube both sides. Everything's trapped under the cube root, so we got to cube both sides right away. So we'll get x cubed equals 7 plus y. Now to get y all by itself, subtract 7. Oh, before I finalize my answer, remember how at the beginning we changed f of x to y? Now we want to name this as the inverse, so we're going to replace y with f inverse. And so f inverse of x equals x cubed minus 1.
It's minus 7. You just slightly erase the top of the cell.
Yeah, thank you. Minus 7. Sorry, thank you. Good thing we have Emily up here at the front. Don't let me go through a whole problem doing things wrong. I'll be mad at you. Okay. You are also going to be asked about domain and range. So you can use your graph and your graphing calculator to help you with domain and range. You can also use your previous knowledge or the pink sheet with the 8 basic functions on it for domain and range. The inverse is a cubic function. That's on your pink sheet. If you have a cubic function, your domain and range is all real numbers for both. And remember that domain and range should really just be switched from the original function to the inverse function. So we would expect domain and range of our original problem to also be all real numbers for both, which it is. A cube root function, if you remember from algebra 2, also has domain and range of all real numbers. Okay, now, you could certainly go to your graphing calculator for the next example and type in that group of parentheses, x plus 1 squared. This would be a good example for us to kind of talk about. If you don't have access to the graphing calculator at all times, do you know what that graph looks like? Describe that graph for me. It's a parabola shifted from its parent graph, so it goes left 1. Okay, so I can imagine what that graph looks like. A parabola shifted left 1, something like this. Does this pass the horizontal line test?
No.
No. Does it have an inverse function?
No.
No. You're done. Do anything else?
How come on the first one you can't have negative 7? Or like you do put negative 7, like for the domain.
Because, are you talking about the original or the inverse?
Yeah.
If I go back to my picture of my graph for the original function there on our first example, oops. When I look at that graph, notice it's going all the way left, it keeps going, it's going all the way right, it's continuous in between, it's all real numbers for domain. So when one side's going left and one side's going right and you're continuous in the middle, all real numbers. Okay. A cube root, you can take cube roots of odd numbers where you can't take square roots of odd numbers. Okay, so it's not a square root function. Okay, a couple other examples. F of x equals the square root of x plus 1. I'm pretty confident this one would be pretty easy to type into our graphing calculator as well. So I'm just going to model for you. If you didn't have the graphing calculator, you'd think about the square root function. Okay. If it has an x plus 1, it's going to the left one, so it looks something like this. Will that pass the horizontal line test? Yes, so we should continue with finding the inverse. Replace f of x with y. Switch x and y. Solve. Square both sides. You're going to get something like x squared equals y plus 2, and then subtract 2 from both sides.
Minus 2.
I think I did that first hour too. I'm having a hard time. Oh, it's not 2. Gosh. Are you pleased now? Is that good for you? Jeez. I'm having a hard time this morning. I don't know why.
Feels like a minute.
Yeah, maybe. This is an interesting one where let's talk about domain and range, and then we'll look at what that means graphically. So if we go up here to our original function, what's the domain of this square root function?
Negative 1 to a positive infinity.
-1 to a positive infinity. And the range would be, starts at 0, goes to positive infinity. So remember, square root functions are restricted on the domain and also the range, which if we apply that down here and we just say, oh, because we switched x and y, we're switching our domain and range, then my domain is now 0 to infinity and -1 to infinity for my range. Which, if you think about the graph of this shape, we would argue it's also quadratic, so it's a parabola, but it's going down 1, so it looks something like this. In terms of the actual graph of what we have right here, the range is fitting, starts at -1, goes to positive infinity, but the range we would normally say is all real numbers. The issue here is we decided on the last slide that quadratics didn't have inverse functions because they didn't pass the horizontal line test. But if you only have the positive square root of x plus 1, you should have an inverse function because you only have one arm of the parabola. So what we're saying here is this should really be restricted so that x is 0 or anything greater. And then think about that on this picture. That would be this part of the parabola. Is that a reflection over the line y equals x? Yes, it is. Okay? It reflects onto itself. Okay. So there's one really important thing you need to do in this case. When the domain of your inverse is different than the domain of the actual inverse function that you have listed, you're going to say for x is greater than or equal to 0. Okay, so that's that little statement there behind your function is really important. Oh, and I forgot to rewrite it with an f inverse, didn't I? So I'll just erase my y and make it f inverse. So my inverse function is actually all of this. On a test, if you didn't restrict the domain there, you would lose a point, okay, because that's important to note. Does anybody have any questions about that? I'm going to flip back to the other side just really quickly. If I had put on this second example a comma and said for x is greater than or equal to -1, then it would have passed the vertical line test, or sorry, the horizontal line test, and you would have been able to find the inverse function. Okay, so watch out for those little restrictions and make sure that you have them if you need them. Quadratics or even functions, even degrees are going to be the big issues there. Okay, last one. This is a really important one to put in your notes. I'll say this is one of the more challenging inverse function problems. So when you look at your homework assignment tonight, make sure that you're doing all of those that look like rational functions. I'm going to graph this in my calculator so we can see how I would graph f of x equals 5 minus x over x plus 2. So I'm going to show you my graphing calculator. See if it passes the horizontal line test. If I go to my y equals menu and I want to have like a numerator over a denominator. Some of you guys have math print, which will do that for you. So you'll actually see like a top and a bottom of a fraction. If your calculator doesn't have the math print capability, then you need to group your numerator with parentheses and group your denominator with parentheses. What was the numerator? 5 minus x?
Yeah.
5 minus x. Close my parentheses for my numerator, divided by x plus 2. X plus 2. Oops, need parentheses. X plus 2. So that my numerator's in a set of parentheses, my denominator's in a set of parentheses. Like I said, some of you have math print, so you don't have to worry about that. I'm going to graph it. I know it's on Zoom 6. Does this graph pass a horizontal line test? Yes, it does. We described those as hyperbolas last year. Okay, and notice that if you'll remember these graphs, you have two issues. You have a vertical asymptote, you also have a horizontal asymptote. So if we're talking about domain, it looks like my vertical asymptote is at -2. So my domain is going to be everything except -2. And for range, it looks like I might have a horizontal asymptote at -1. So it's going to be everything except -1. I'll show you how to verify that in the function here, but you can see that in the graph. Okay. So I'm going to go ahead and say it does pass, so I am going to go forward with the inverse. For domain and range, as a quick review from Algebra 2, your domain is restricted by a vertical asymptote, which is found by setting your denominator equal to 0. You can't divide by 0. So -2 makes the denominator equal 0. That's the restriction to the domain. So I would say -infinity to -2, -2 to positive infinity for domain. For range, you're restricted by your horizontal asymptote because that's a y equals line. And to figure out your horizontal asymptote, you have to compare the degrees of the numerator and the denominator. So the degree of the numerator, the highest exponent is 1. The degree of the denominator is also 1. And when they're equal, the horizontal asymptote is the ratio of their leading coefficients. So -1 over 1. So you have a horizontal asymptote at -1, which means that gets excluded from your range. So I've identified domain and range. That's a good review of how to do that. Now I'm going to go forward with my inverse. When I switch x and y, notice I have two x's. So I have to replace both of the x's with the y. And we want to put our focus on, we're trying to get y all by itself. Okay. What are some ideas from you guys about what you might do to manipulate this equation and get y all by itself? Emma, you've got one idea to start us off.
Multiply both sides by y plus 2.
Yeah, let's get rid of this fraction thing, right? So we're going to multiply both sides by a y plus 2. So I have x times y plus 2 equals 5 minus y. Okay. Again, put your focus on trying to get y all by itself. Add y to both sides. So now it's kind of like when you think back to multi-steps in Algebra 1, you want all the x's to be on one side, you want all the numbers to be on the other side. So we could add y to both sides. This kind of gets us to what feels like a wall a lot of times. The trouble spot right here is this group of parentheses. The only way to undo that multiplication, x times y plus 2, is division, and that doesn't really help us with anything so far in our equation. So how else can we get rid of parentheses? Let's distribute. So this is going to be an interesting piece. You're going to distribute into whatever it is you multiplied from the denominator. So we'll get xy plus 2x plus y equals 5. And we can kind of run back to Emily's idea where she had added y to get it on the same side as the other y. Now let's move the 2x so it's no longer over there, because 2x isn't part of y and we're trying to solve for y. Okay, so let's subtract the 2x from both sides. So you get xy plus y equals 5 minus 2x. Okay, or negative 2 plus 5. Negative 2x plus 5. Can you add xy plus y? No. But what's nice about those two things? They both have y. So up here, you're going to distribute so you can factor out a greatest common factor. So down here, you can say, let me take a y out of both. Now, can you solve for y?
Yeah.
Yeah, you divide. And you're trying to say, oh my gosh, it's going to look like another rational function. So the inverse of a rational function is another rational function. So we'll divide by x plus 1. And we'll have 5 minus 2x over x plus 1. And we can rewrite that f inverse 5 minus 2x over x plus 1. Now, remember that domain and range should be switched. Okay. Here, the domain is everything except -1, which used to be our range. When we look at the degrees, they're even. When we look for the horizontal asymptote, it would be -2 over 1. So -2 is excluded from our range, which used to be our domain. So it works out with the vertical and the horizontal asymptotes. Practice those for sure on the homework assignment. Okay, it's on the gold sheet. And where appropriate clothing tomorrow, we're going to be doing function aerobics.
Just
We just do one.
it's always second out.
You don't